function into subintervals using sample points and the sample points we defined where x0 is a, we have x1, x2, x3 all the way up to xn, which would equal to b. And as the number of rectangles increase, the area under the curve becomes more accurate. So, and we have the lower sum, which is typically an underestimate. And the lower sum has approximation rectangles strictly under the curve, in the sense none of the rectangles would go above the curve or past the curve. Everything would be under, and the upper sum is typically the overestimate, has approximation rectangles that go over the curve. And we sort of gave a limit definition, but for now I'll just call this Ln and LRn. The sample intervals are of length delta x is equal to b minus a divided by n. And we also noted that limit n approaches infinity, if we have infinitely many rectangles, the right or the lower sum, the upper sum would both equal to the area under the curve, and that would be the true area under the curve. So now we are going to define a definite integral. A definite integral gives us the area under the curve. So when we say it gives us the area under the curve, it gives us the exact area under the curve. So what is a definite integral? So integral f of x dx is called the definite integral of the function f of x on the interval a comma b. So here that is the lower limit, and that would be the upper limit. And by all means, this is equal to limit n approaches infinity, sum I equals 1 to n, f of xi multiplied by delta x. So delta x, or we can even call it as delta xi, because delta xi need not always be the same. They can be different, but in our case, the left sum and the right sum, we've had fixed subintervals that delta x were identical. So those are simply values of the function evaluated at the sampling points. And delta xi is simply the width, or length, I'll just call it as length. And keep in mind that delta xi need not be the same, but we typically assume that the delta xi are the same when it comes to finding a definite integral. So what we know is that the definite integral is directly related to the area under the curve, and some of the things that we've got to know about a definite integral, when we integrate a to b f of x dx, so whatever x that I see must also be there. So, and that x is the independent variable. So for instance, I could have another function on a to b. I could have g of t times dt. So here you can see those two numbers are exactly the same, and t is the independent variable. Another thing to note is when we integrate a to b, f of x dx will result in a number. Because a definite integral gives the area under the curve. So if the curve is above the x-axis, the area will be positive. If the curve is below the x-axis, the area will be negative. The definite integral gives the total or net area under the curve. Now I'll illustrate this using a graph. Suppose we have a curve of that sort, and this is the function f of x, and we want to find integral a to b f of x dx. When we perform this operation, let me go ahead and do the areas here. So the one in purple, I'll call it A1, A2, A3, B1, B2, B3. So the net area that we get when we integrate would simply equal to A1 plus A2 plus A3 minus B1 minus B2 minus B3. So the ones above the x-axis would give us a positive area, and the ones below the x-axis would give us the negative area. We know that the area under the curve is going to be given by approximating rectangles and summing the areas of each of the rectangles. And we know that the sum, I will just call it Rn, is sum I equals 1 to n f of xi times delta x, where delta x is simply b minus a divided by n. So n would simply be the number of sampling points on a comma b. A is the lower endpoint of the interval. B is the upper endpoint of the interval. And we can find xi as simply a plus I times delta x, i.e. x0 would simply be a plus 0 times delta x, which will give us a. x1 would be a plus 1 times delta x. That would give us a plus delta x. x2 would equal to a plus 2 times delta x. That is a plus 2 delta x, and so on. Now, if we take the limit n approaches infinity, we increase the number of sampling points from a fixed number to infinitely many endpoints, Rn, then we would simply have limit n approaches infinity, sum I equals 1 to n, f of xi times delta x. Now this sum is what we call the Riemann sum. And what would that equal to if we define it in this way? Then this would simply equal to integral a to b f of x dx. And clearly a is the lower limit of integration. And b is the upper limit of integration. So anytime we talk about a definite integral, we are referring to the Riemann sum. So the limit n approaches infinity, sum I equals 1 to n f of xi times delta x, which is the Riemann sum, is the area under the curve, and it is the value of the integral of the function f of x dx between the limits of integration a to b. So that would simply be equal to the area under the curve. Now we're going to find the area under the curve using the Riemann sum approach and directly using some properties, just like we had the derivative of sine x, we had cosine x, derivative of cosine x, we ended up getting negative sine x. So we took the limit of the difference quotient to find the derivative of a function. So the idea is the same. We take the limit of the Riemann sum to get the area under the curve. But finding the difference quotient each and every time to find the derivative, it's time consuming. Which is why we have properties and formula for certain derivatives, and we can simply make use of those formulas to find the derivative of the function. Same argument applies here. Even though we can evaluate this sum to get the exact value of the integral of the function, finding the sum each and every time is time consuming. So we need to have an easier way, and if you look in advanced calculus books, your book might have it. We have a table of integrals for many functions that we know. A key thing, let me show an example on how to write a function in terms of the Riemann notation. So for x in 0 to 2 pi. So what we're trying to find is integral 0 to 2 pi sine x dx, which is simply limit n approaches infinity, sum I equals 1 to n. What is f of x? Well, f of xi times delta x. That is simply limit n approaches infinity, sum I equals 1 to n. Instead of x, we're going to rewrite it as xi multiplied by delta x. Here, delta x is b minus a divided by n. b is 2 pi, a is 0, divided by n, so we have 2 pi over n. So integral 0 to 2 pi sine x dx in Riemann sum notation is simply limit n approaches infinity, sum I equals 1 to n sine xi times 2 pi divided by n. So that would equal to limit n approaches infinity, 2 pi over n times sum I equals 1 to n sine xi. So that is the definite integral that we're looking for, and that is the corresponding Riemann sum that would give us the exact value of the integral. By all means, that is going to give us the area under the curve. Before we delve into finding Riemann sums and approximating definite integrals using Riemann sums, it is important to know a few sums. And these sums would come into play when we try to evaluate Riemann sums. So what are those? The sum of n natural numbers. What do we mean by that? Suppose you want to sum numbers 1 through 5. And we clearly know that it's 9, 12, 14, and 15. The answer is 15. But what if you want to sum from 1 all the way up to 100? We don't want to sit here and add it manually. So it's given by a simple formula. The formula is I equals 1 to n, I. And that is simply n times n plus 1 divided by 2. The n in our example would be 5. So we would get sum I equals 1 to 5, n, to be equal to this formula, n times n plus 1 over 2. Oh, sorry, must be I, not n. Which is 5 times 5 plus 1 divided by 2, which is 5 times 6 divided by 2. You get 15. So as another example, suppose I want to sum 1 to 100, you don't have to sit and add everything. All I have to do is 100 times 100 plus 1 divided by 2, which is 50 times 101, which would give us 5,050. So that's pretty straightforward. In a similar way, sum of squares of n natural numbers is given by this formula. I equals 1 to n, I squared is simply n times n plus 1 times 2n plus 1 divided by 6. Now, let's say we have As an example, we want to sum 1 squared plus 2 squared plus 3 squared plus 4 squared. That is 5, 14, and 25. Oh, 9, 14, sorry, not 25, that's bad math. It's 9, 14, and 16, it's 35. So our sum would be I equals 1 to 5, I squared, 1 to 4, I squared, which is simply 4 times 4 plus 1, 4 times 2 plus 1 divided by 6. That would give us 4 times 5 times 9 divided by 6. And we know 9 times 4 is 36. That would go 6 times, and you get 30. Did I add something wrong here? 4, 5, 14, 16. Oh, bad math indeed. So you can correct yourself. It's 30. So in a similar manner, if we want a sum of cubes of natural numbers, as an example, let's say we want to do 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. We have 1 plus 8 plus 27 plus 64, and that would be 91, 92, we should get 100. That is given by this formula, 1 to 4, n is 4, I cubed, which is n times n plus 1 over 2 squared. And that is simply 4 times 4 plus 1 divided by 2 squared. You get 2 times 5 squared, which is 10 squared. We get 100. So these formulas make or give us the opportunity to evaluate sums easily. There are a few properties of sums also. Sum I equals 1 to n, some constant multiplied by ai would mean we can pull the constant out and we can simply sum ai. Keep in mind the index is from I equals 1 to n, so it is going to only affect the term that has I in it. So the c, which is a constant, will simply come out. So if we have sum I equals 1 to n ai plus bi, then we can split it up and write it as I equals 1 to n ai plus sum I equals 1 to n bi. Suppose we have I equals 1 to n and we simply add 1s. So in this case, we would get the answer to be n. As an example, if we have sum I equals 1 to 5, 1, this means I am summing 5 1s, which would give me 5. So that answer would match up that answer if the sum is I equals 1 to n, summing simply 1. So these are some of the sums that we need to know, especially when we try to evaluate Riemann sums. Here is an example where we want to evaluate the Riemann sum with n equals 6, taking sample points to be left endpoints. And what would this Riemann sum represent? And we want to illustrate with a diagram. So a calculator will come handy in a problem like this. So have the calculator on our side. We know what cosine x looks like, but I'll just go ahead and plot cosine x. From 0 to 3 pi over 4, and we know that cosine simply goes between -1 and 1. And if we graph this, and that is the curve that we get. That point right there would be 3 pi over 4. Cosine pi over 2 is 0, and that would be 0. The value up there is 1, and this is the value at cosine 3 pi over 4. That would be negative 1 over square root of 2. So the first step is for us to determine the sampling points. So in other words, we need to find delta x. Delta x is b minus a divided by the number of sampling points. B is 3 pi over 4. A is 0. So we have 3 pi over 4 minus 0 divided by n, which is 6. Which would give us 3 pi divided by 4 times 6, which is simply pi over 8. So our first endpoint, x1, would be pi over 8. The second endpoint is pi over 8 plus 2 times delta x. I guess we'll start at 0. So the first one would be a, which is 0, plus 1 times pi over 8, which would give us pi over 8. I'm using the formula xi is a plus I times delta x. A is 0, I is 1, and delta x is pi over 8. x2 is 0 plus 2 times pi over 8, which would give us pi over 4. x3 is 0, starting point, 3 times pi over 8. That would give us 3 pi over 8. x4 is 0 plus 4 times pi over 8, which would give us pi over 2. x5 is 0 plus 5 times pi over 8. We will have 5 pi over 8. x6 is equal to 0 plus 6 times pi over 8, which is 3 pi over 4. So now that we know our endpoints, the first endpoint is at pi over 8. So pi over 8 is probably there somewhere. The next one is pi over 4. The next one is 3 pi over 8. Then we have pi over 2, of course. And on the other side, we have 5 pi over 8. And the next one is simply 3 pi over 4. So we have our 6 endpoints. One of them is exactly at pi over 2, and the other one is 3 pi over 4. Now, they want us to start from the left-hand side, the left endpoint. We could have started at x0, and we could start from the value x0 and go from there. So let me put another point here, because I see that we could have another rectangle. So x0 would be 0, which is the starting point. So we'll have 0, which would be that point right there. So now we have to draw our rectangles. So the first rectangle would go from there to there. The second rectangle from that point over there. The third rectangle would start from that point to over there. The fourth rectangle from there to over there. The fifth rectangle would start from here, but the left end point, since it's over there, we have to sort of use the right one because it's decreasing, so we'll have that. And the next one would be from there to over there. The reason being, we want to take sample points to be left endpoints, so I'm taking only the left values. If I did the right values, then I will get a different answer. There are multiple ways to approximate this. Let me undo this. Wouldn't let me do. Okay, so one may argue, well, this left endpoint simply goes over there, so I can't compute any. So that's fine, and we can start from there and go that way. So those are my rectangles. Now I know the x1 values, I know the x0 values. So x0 is right here, x1, x2, x3, x4, x5, x6, and I can't go past 3 pi over 4, so that's all I would have. The Riemann Sum Definition, R6, is some, I'm going to start at 0 to 6. I have 6 endpoints, f of xi multiplied by delta x. Delta x is constant in this problem, which is pi over 8. So sum I equals 0 to 6. F of xi times pi over 8, and we know that pi over 8 is a constant, and based on the properties, if we have a constant inside the sum, we can pull that constant out. So we have pi over 8 sum I equals 0 to 6 f of xi. So our objective now is to evaluate pi over 8. I starts at 0, so f of x0 plus f of x1, because I is 1, f of x2, f of x3, f of x4, f of x5, and f of x6. So the first term we have to evaluate. So we know x0 is 0, so I'll do f of 0. F of 1 is pi over 8. F of 2 is x2 is pi over 4. F of x3 is 3 pi over 8. F of x4 is f of pi over 2. x5 is 5 pi over 8, so 5 pi over 8. Plus f of x6 is f of 3 pi over 4. So I'm going to set my function as cosine x, and I'm going to go back here to second table. I believe I didn't press table. Before we do the table, let's do table set. Second window. We're going to start at 0. I'm going to change the independent value to be asked, or you can do delta table, which would be in our case delta x. So I will simply plug in second pi divided by 8. And then we can simply put second table, and it is going to evaluate the values that we need. So at 0, we have 1. Pi over 8 is the next number, so we have 0.92388. Pi over 4 is the next number, which is 0.70711. 3 pi over 8 is the next number, 0.38268. We know that f of pi over 2, cosine pi over 2 is 0, so we have 0. And the next one is f of pi over 8, which would give us negative 0.3827. Mind you, the last one has to be 0 because I can't have a rectangle there because the function stops at 0. So we can't include that part, so I'm just going to put 0. Add all these values. 1 plus 0.92388 plus 0.70711 plus 0.38268 minus 0.3827. That gives me 2.63097 multiplied by pi and divide by 8, we get 1.03318. Now, what does this tell us? This simply is giving us an approximation of the area here minus the area there. So what we're finding is A1, the shaded area there, minus A2. So whatever we found using the Riemann sum is merely the area A1 minus A2. So here is an example where we have a function g of x which is shown by this graph, and the intervals are from minus, or the interval of the function is from -4 up to positive, sorry, it's -2 up to positive 4. And we want to find the integral of g of x between -2 to 4. Now, in the previous problem, the area, net area that we found, A1 minus A2, is merely the integral of 0 to 3 pi over 2, 3 pi over 4, f of x dx. Not exactly, but approximately, which is integral 0 to 3 pi over 4 cosine x dx. Here we simply have g of x instead of cosine x. So we have to do the same process. We have to estimate the value of the integral using right endpoints, left endpoints, and midpoints. So let's first start with finding delta x. What is delta x? Delta x is simply b minus a divided by n. They've said that n has to be 6, so b is 4, a is -2 divided by n, which is 6, so we end up having 6 over 6, we get 1. So the endpoints are -2, -1, 0, 1, 2, 3, and 4. Those are our 6 endpoints. So now we have to evaluate the integral using the right endpoints, then the left endpoints. The nice thing about Riemann sums is that we don't have to sketch the rectangles like we did in the previous problem. So here it says, oh, we've got to start with the right endpoints. If that is the case, all we have to do is start at the endpoint 4 and evaluate all the way up to -1. So what do we mean by that? So we have 6 subintervals. So we have x1, x2, x3, x4, x5, x6. So x1 in this case would be, well, we'll start backwards. x6 is 4 because right endpoint, then 3, 2, 1, 0, and -1. So that is for the right endpoint case. And what does Riemann sum state? the right sum here, R6, would simply equal to delta sum I equals 1 to 6 f of xi multiplied by delta x. So that would mean delta x is 1, so sum I equals 1 to 6 f of xi. So all we are trying to find is f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5 plus f of x6. So we have f evaluated at -1 plus f evaluated at 0, f evaluated at 1, f evaluated at 2, f evaluated at 3, and f evaluated at 4. I'm simply plugging in x1, x2 all the way up to x6. So I can pick those values from the graph from looking at it. This is negative 3 over 2 plus 0, positive 3 over 2 plus 1/2 plus 1 plus 1/2. So the answer is 0. So the net area, the positive areas cancel out the negative areas, we end up getting 0. Now we have to do the same with the left endpoints. So x1, x2, x3, x4, x5, and x6. Since we are starting on the left-hand side, the first point would be -2. And the next one would be -1, 0, 1, 2, 3, because delta x is 1. So L6 is sum I equals 1 to 6, f of xi times delta x. Delta x is 1, so 1 to 6, f of xi, which in this case is f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5 plus f of x6. So we get f of -2 plus f of -1 plus f of 0 plus f of 1 plus f of 2 plus f of 3. f of -2 is 0. f of -1 is -3 over 2. f of 0 is 0. f of 1 is positive 3 over 2. F of 2 is 0. And f of 3 is negative 1 over 2. So the answer here is negative 1 over 2. And lastly, we have a case where we have to use midpoints. So when we say midpoints, we're talking about the midpoints of each subinterval. So we are looking at the midpoint there. Midpoint, midpoint, midpoint. Okay, and 2, 2.5 right over there, 3, 3.5 right over there. So in this case, we're simply evaluating at the midpoints. So here, delta x still is 1, because from one midpoint to another, delta x is simply 1. So what are the midpoints? we have negative 3 over 2, negative 1 over 2, that is the midpoint between negative 1 and 0, positive 1 over 2, midpoint between 0 and 1, 3 over 2, midpoint between 1 and 2, 5 over 2, midpoint between 2 and 3, and lastly the midpoint between 3 and 4, which would be 7 over 2. So we have sum I equals 1 to 6, f of xi times delta x is still 1, so we have I equals 1 to 6, f of xi. So that would equal to f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5 plus f of x6. So minus 3 over 2 minus 1 over 2, f of 1 over 2, f of 3 over 2, f of 5 over 2, and f of 7 over 2. We go back here and we look at each value. So we have to pick the values. This has to be 3 over 2. Okay, so at negative 3 over 2, we have a value of negative half. Same at negative 1 over 2. At positive half, we have 1. And 3 over 2, we have 1. At 5 over 2, we have a value of 0. And at 7 over 2, that is between 3 and 4, we have negative half. So if we combine everything, we end up getting 1/2 as the answer. So the net area, we have 0, one case, negative half, and the other case, midpoint, 1/2. So we're getting different answers here. But if we evaluate it by increasing and limit n approaches infinity, several approximating rectangles, we could come up with a better estimate for the area. So we actually sort of used the midpoints previously in that example. So we could formalize this as what we call the midpoint rule. So suppose we have a function f of x defined on the interval a comma b. We know delta x is simply b minus a divided by n. That is simply the number of sample points. So if we have a and b, we simply divide it as x1, x2, x3, too many dots there, xn minus 1, xn, and so forth. So what the midpoint rule states is that we pick midpoints. I can denote this x bar 1, which is the midpoint between x1 and x2. X bar 2 is the midpoint between x2 and x3. And x bar n is the midpoint between xn and x minus 1. So x bar 1 is simply 1/2 of x1 plus x2. x2 bar is simply 1/2 x3 plus x2, all the way up to xn bar is 1/2 xn plus xn minus 1. So now we could define the Riemann sum, I'll call it Mn, is simply sum I equals 1 to n, the function evaluated at each of those midpoints multiplied by delta x. And that is going to approximate the integral of f of x dx, which is the same as saying the area under the curve f of x defined on the interval a comma b. So here is an example on midpoint rule where we have to approximate the integral using n equals 5. So a is 0, b is 1. That is our function f of x. N is given in the problem. So delta x is simply b minus a divided by n. So 1 minus 0 divided by 5. So we have 1/2. So first we've got to get midpoints. It's bad math there. It's not 1/2, it's 1/5. For a minute there, like, what just happened? So it is 1/5. So we have 0, 1, 1/5, 2/5, 3/5, 4/5, and 5/5 is simply 1. So those are our subintervals. So our midpoints are going to be between 0 and 1/5. So I could call that x bar 1. So that is simply 1/2 times 1/5 plus 0, which is 1/10. X2 bar, so x2 bar is 1/2 times 1/5 plus 2/5. That would give us 3/10. And x3 bar (1/2) 2/5 plus 3/5, which is simply 1/2. x4 bar is between 3/5 and 4/5. 1/2 3/5 plus 4/5, which is 7/10. x5 bar is between 4/5 and 1, so 1/2 4/5 plus 1, that is 1/2 times 9/5, we get 9/10. So all we have to do is evaluate the function. So 1 to 5, f of x bar I multiplied by delta x. We know delta x is 1 over 5. So 1 over 5, sum I equals 1 to n, f of x bar I. We know the function, so let's go ahead and enter the function in the calculator. X cubed plus 1, and we can go to table set, and we're starting at 0 going all the way up to 1, and I'll simply set delta x is 1 over 5, which is 0.2, and I'm just going to evaluate the table. It's giving us all the values, so 1 over 5 when it is, oh my bad, we have to table set at midpoints, so it's at 0.1. So at 0.1 we have 1.0005. At 0.3 we have 1.0134. At 0.5 we have 1.0607. At 0.7 we have 1.1589, and lastly at 0.9 we have 1.3149. So add all the values: 1.0005, 1.0134, 1.0607, 1.1589, 1.3149, divide by 5, the answer is 1.10968, which we can approximate to 1.1097. And that is the midpoint rule. Here is another problem on midpoint rule. We have A as 0, B as 2, and N is 5. So delta x is simply B minus A divided by N. So 2 minus A, 2 minus 0 divided by 5. So we have 2 over 5. The function here is x over x plus 1, and we are trying to approximate the integral using the midpoint rule. So first we've got to find the midpoints. So we have 0 to 2, 2 over 5, 4 over 5, 6 over 5, 8 over 5, and 10 over 5 is simply 2. So what are the midpoints? The midpoint there is 2 over 5 divided by 2, which is 1 over 5. The midpoint there would be 3 over 5. Midpoint there would be 1. Midpoint there would be 7 over 5. And midpoint there would be 9 over 5. So x1 bar is 1 over 5. x2 bar is 3 over 5. x3 bar is 1. x4 bar is 7 over 5. and x5 bar is 9 over 5. So what does the rule state? The rule simply states the integral 0 to 2 x over x plus 1 dx can be approximated by evaluating the function at the midpoint and multiplying by delta x. Delta x in this case is simply 2 over 5. So you can pull 2 over 5 out. So what we can do now is use the calculator to get the midpoint values. The function is x divided by x plus 1. And we can go to table set. We are starting at 0. And we will just increment it by 1 over 5. We have to pick every other value. So in other words, we have f of 1 over 5 plus f of 3 over 5, f of 1, f of 7 over 5, and f of 9 over 5. So 2 over 5, f of 1 over 5 is 0.16667. 3 over 5 is 0.375. F of 1 is 0.5. F of 7 over 5 is 0.58333, and f of 9 over 5 is 0.64286. Add all the values together. Multiply by 2 over 5, we get 0.9071. Therefore, the integral 0 to 2 x over x plus 1 dx is approximately equal to 0.9071. So here we have a problem where we've got to use the form of the definition of the integral given in Theorem 4 to evaluate the integral. By Theorem 4, I am referring to Theorem 4 in the textbook. The textbook details are on the first page. It's pretty much giving us the definition of Riemann integral and using a Riemann integral to or the Riemann sum to come up with the integral or the value of the integral. So first we've got to find delta x. So delta x is simply 2 minus 0 divided by n. So we simply have 2 over n. And we know the integral is approximated by a Riemann sum I equals 1 to n f of xi multiplied by dx. Delta x is simply 2 over n. So we could pull that 2 over n outside. We are going to plug in xi for x in the function, so 2xi minus xi cubed. We know that if we have two terms in a sum and there is a plus or minus, we can split the sum up. And we also know that if we have a constant multiple, such as the 2 over there, we can pull that 2 out as well. And that's what we would have. Now the key to note here is how we come up with xi. If you recall that xi is defined in terms of a, the initial value, plus I times delta x. And that's just how we increment it. So I can write this as 2 times sum I equals 1 to n, a plus I delta x minus sum I equals 1 to n, a plus I delta x raised 3. And we know that a is 0. And that would give us 2 over n, 2 sum I equals 1 to n, I delta x, minus sum I equals 1 to n, I cubed delta x cubed. Delta x, once again, is a constant. And we know that that is 2 over n minus 2 over n cubed. 2 over n is a constant multiple. It doesn't depend on I, so I'm going to pull it outside of the constant. So 2 times 2 over n is 4 over n. Likewise, 2 over n cubed is 8 over n cubed. 2 cubed is 8. So 8 over n cubed, sum I equals 1 to n, I cubed. This is where the important sums that I mentioned earlier, or over here, comes into play. These are the formulas that we're going to make use of in order to come up with the Riemann sum. So we know sum of n natural numbers, it's simply n times n plus 1 over 2. Here it is n times n plus 1 over 2 squared. We have n times n plus 1 over 2 in common, so 2 over n times n plus 1 over 2 multiplied by 4 over n minus 8 over n cubed times n plus 1 divided by 2. So the n's would get cancelled, the 2 would get cancelled. So n plus 1 times 4 4 over n minus, I can cancel those, 4 over n squared times n plus 1. We've got to take a common denominator, so n plus 1 times 4n over n squared minus 4 over n squared times n plus 1. So the common denominator is n squared, so 4n minus 4 times n plus 1 over n squared, which would give us n plus 1 times 4n minus 4n plus, minus 4 divided by n squared. So those two would go away, and we'll have n plus 1 times minus 4 over n squared. Now, the Riemann Sum Theorem states that integral 0 to 2 to x squared minus x cubed dx would equal to the limit n approaches infinity. The formula up there, which is Rn, sum I equals 1 to n, f of xi delta x. That's exactly what we found over there. So I could write that as, if I pull n out, I have n times 1 plus 1 over n minus 4 over n squared. And I want to take the limit of n approaches infinity. But before I apply the limit, I'm going to cancel those. Limit n approaches infinity, 1 plus 1 over n times minus 4 over n. So the limit is going to affect that term and that term. So we would end up having 1 plus 0 times 0. The answer is 0. And that is the integral. Later on, when we know more about integrals, you will see when you integrate this, you would get 0. So here is a problem where we have to find an approximation to the integral using a Riemann sum with right endpoints, and also using the definition, which is taking the limit of the Riemann sum to evaluate the integral. Clearly, using the definition in Theorem 4 and evaluating the Riemann integral is going to give us the exact value of the integral. So delta x in this case is b minus a divided by n. They have specified n is equal to 8. This would mean delta x is equal to 4 minus 0 over 8, which is 1 over 2. Zero, 4, and the endpoints would be 1/2, 1, 3/2, 2, 5/2, 3, and 7/2. So we are looking at the right endpoints. So what we have to do is select 4, 7 over 2, 3, 5 over 2, 2, 3 over 2, 1, and 1 over 2. And if you look at it, that would be 8 points. So our 8, using the right endpoints, would be sum I equals 1 to 8, f of xi times delta x. Delta x is simply 1/2, so I'm going to pull that out of the sum. F of x8. That would simply be x1, x2, x3, x4, x5, x6, x7, x8. I'm going to make use of the calculator. Minus 3x, table set. When it start at 0, go all the way up to 4, and the increments here is 0.5, which is 1/2. So I'm going to go back to my table. I have the values. So 1/2, we don't include the first one, so minus 1.25, minus 2, minus 2.25, minus 2, minus 1.25, 0, 1.75, and the value at 4, which is 4. So let's sum all that. So we have negative 1.25 minus 2 minus 2.25 minus 2 minus 1.25 plus 1.75 plus 4, get minus 3, so minus 1.5. And that's what we would get when we simply use Riemann sum with right endpoints and n equals 8. That is 5. Now we're going to move on to using theorem 4. So using theorem 4, which simply means we have to take the limit n approaches infinity of the Riemann sum, and in this case delta x is b minus a divided by n, so we have 4 over n. So let's find the sum first. Sum I equals 1 to n, f of xi, delta x. Sum I equals 1 to n, f of xi, times 4 over n. I equals 1 to xi, f of xi. Now we know that xi is a plus I times delta x, and a is 0 in this case, so we would simply have 0 plus I delta x, so we would have I times delta x. We're going to plug in xi in the function, so 4 over n, sum I equals 1 to n, I delta x plugged in the function, we have I delta x squared minus 3 times I delta x. We know that we can split the sum because there is a difference. So we can write this as I equals 1 to n, I squared, delta x squared, minus sum I equals 1 to n, 3i delta x. The delta x is a constant, so we can pull that out. The 3 delta x is a constant in the second sum, so we can pull that out. So delta x squared is 4 over n squared. Sum I equals 1 to n I squared minus 3 times 4 over n. Sum I equals 1 to n I. We know from the sums earlier, the sum of squared natural numbers is n times n plus 1 times 2n plus 1 divided by 6. The sum of n natural numbers is n times n plus 1 over 2. We can cancel the n out. 8 and 3, 6. N goes away. So we have 4 over n, 8 over 3n times n plus 1 times 2n plus 1 minus 6 times n plus 1. We have the n shouldn't be there. We have n plus 1 in common and a 2 in common, so 2 times n plus 1, I could pull that out, 4 over 3n times 2n plus 1 minus 6 times n plus 1. So before I take the limit, I'm going to rewrite this as 4 over n times 2, pull n out, 1 plus 1 over n, 4 over 3n, pull the n out, n times 2 plus 1 over n, minus 6, pull n out, 1 times 1 over n. The n's here would get cancelled. The n there would get cancelled. So we would have 8 times 1 plus 1 over n multiplied by 4 over 3 times 2 plus 1 over n minus 6n times 1 plus 1 over n. I feel like I made a mistake here somewhere. I see. When I pulled the n plus 1 out, I pulled it out of the first term, but I didn't do it here. So it should just be 6, so that term will not be there. So we would end up having 8 times 1 plus 1 over n multiplied by 4 over 3, 2 plus 1 over n minus 6. We could take, so this is simply our n. So limit n approaches infinity, our n would be 8 times 1 plus 1 over n multiplied by 4 over 3 times 2 plus 1 over n minus 3. So when we take the limit, that term is going to go to 0. That term would become 0 because we have 1 over infinity. So we would have 8 times 1 plus 0, 4 over 3 times 2 plus 0 minus 3. If we take a common denominator, we have 8. 8 over 3 minus 9 over 3. And that is 8 times negative 1 over 3. So the answer is negative 8 over 3. And that is the value of the integral, the exact value. Now the approximation was negative 1.5. It came pretty close to negative 8.3. Negative 8.3 is about 2.6 something, 6667. So that's what we have. Now we move on to some properties of definite integrals. Of course, a to b f of x dx is the definite integral of the function f of x between a and b. A is the lower limit of integration. B is the upper limit of integration. So the first property, what if a is a constant, f of x is a constant, in the sense f of x is c. So let f of x equals c. So we have integral a to b, c times dx, which would simply be c times b minus a. C multiplied by upper limit minus the lower limit. Suppose we have two functions and we have f of x plus or minus g of x dx, then it simply means we can write the integral of the first function plus or minus the integral of the second function. If we have a constant multiple of a function, we can pull the constant out of the integral and evaluate the integral by itself. That goes back to pulling the constant out of a Riemann sum. It is the same thing. Integral a to b f of x dx is equal negative b to a f of x dx. In the sense, if we switch the limits, then the sign would flip. So I go from a to b to b to a, so the magnitude of the integral would be the same, but the signs will get switched. So if I have integral a to b f of x dx, then I can pick an arbitrary point between c, integrate the function from a to c, then c to b. So what do I mean by that? That property can be seen easily from a graph. So suppose we want to find the area under the curve of that sort. So what we want is that area and that area is simply integral a to b f of x dx. What we are trying to say is if we pick a number, c, I can find the area from a to c, add it to the area c to b, which would be that part. And that must equal to that. So the sum of these two integrals would equal to the sum equal to the area under the curve f of x between a and b. What I'm going to write now are called comparison properties. So suppose f of x is greater than or equal to 0, i.e. the graph is above the x-axis. Then integral a to b f of x dx must be positive. So if it is above the x-axis, it has to be greater than or equal to 0. Now that only works because the function is bigger than 0 for all values of x. And we have to make sure that a is less than or equal to x and less than b. Suppose we have two functions f of x is greater than equal to g of x for a less than or equal to x less than or equal to b. In other words, the function f of x is bigger than g of x for all values of x. So what we're meaning to say that's f of x. That's g of x. And f of x is bigger than g of x for all values between a and b. So the area under f of x is that. The area under g of x is that. Just by looking at it, we can see that the area under f of x is bigger than the area under g of x. So our conclusion is if f of x is greater than or equal to g of x, then integral a to b f of x dx must be greater than or equal to integral a to b g of x dx. And lastly, suppose f of x lies between two numbers, m, lowercase m, and uppercase m, for all values of a less than or equal to x, less than or equal to b, then the integral has to be between m times b minus a and uppercase m times b minus a. Now that can be shown by subtracting the areas, and you can see that this particular inequality will be satisfied. So here we have to evaluate this integral by interpreting it in terms of areas. So we need to have a graph for sure. If we rewrite this function, 1 minus x, y equals f of x, which is 1 minus x, which is the same as saying minus x plus b. Well, minus x plus 1. And that is in the form mx plus b, which we all know is a line. So when x is 0, we are at 1. When x is 1, we will end up at 0. And when x is 2, we will be at minus 1. And we can just draw a line. And when x is minus 1, we are going to be at 2. Let's see, at 2. And that is what we'll have. We can connect the dots. And now they want us to find the integral by interpreting it in terms of the area. So the integral is simply that area minus that area. Now both of them are right-angled triangles. So the first one over here, I'll call it A1. That would be A2. A1 is a area of a triangle, right-angled triangle. So that is 2. So we have 1 unit there, 1 unit there. So with base equals 2 and height equals 2. That would be the height. So we have 1/2 base times height. One half 2 times 2, we end up getting 2. A2 is the area of a right-angled triangle with base equals 1, because that number is 1, so base, length 1. And height, since that is minus 1, height is 1. So height would be 1. Using the same formula, we have A2 is 1/2 times 1 times 1, which would give us 1/2. So the area for integral -1 to 2, 1 minus x dx, is simply A1 minus A2. Reason being A1 is above the x-axis and A2 is below the x-axis, so we have 2 minus 1/2, which would give us 3/2. So what I've done here is I've taken the integral and I've split the integral into 2 pieces, and we're going to consider the first integral. the function x is simply y is equal to x, which is the line passing through the origin. But what you can see is the areas are the same, and one is on the positive side, the other is on the negative side. So the net area is simply A2 minus A1. So A2, A1 both correspond to the area of a right-angled triangle with base 5 and height 5. So we know that the area of a right-angled triangle is 1/2 base times height. So we have 1/2 times 5 times 5 is 25. However, since the areas are the same, we have A1 minus A2, so 25 over 2 minus 25 over 2, we get 0. The second function, or the second integral, is a bit tricky because we've got to know something from algebra. So the equation of a circle is x squared plus y squared is equal to r squared, where r is the radius. So in this case, if we have x squared plus y squared equals 25, we are representing a circle with radius 5. So y squared would equal 25 minus x squared, which would mean y is plus or minus square root of 25 minus x squared. Y would equal y equaling to square root of 25 minus x squared would be the upper semicircle, and y equals minus square root of 25 minus x squared would be the lower semicircle. Now, we are only concerned about the upper semicircle, so let's go ahead and draw that out. So radius 5. Doesn't look like a circle, but you get the point. So we want to find that area. So the area under the curve, square root of 25 minus x squared dx, is simply the area of a semicircle with radius 5. We know the area of a circle is pi r squared. We divide by 2 to get the area of the semicircle, so we have 25 pi over 2. So the area of the integral would simply be 0 minus 25 pi over 2. We get negative 25 pi over 2. So here we have another function. This is the absolute value function. And we know the absolute value function has a V shape. And if we set 2x minus 1 equal to 0, 2x would be equal to 1, x would be equal to 1/2. So at 1/2 it becomes 0. When we have 0, we have the absolute value of -1, which would give us 1. When we plug in 1, we get the absolute value of 1, which is +1. So we simply end up having that V shape. And the area we're trying to find is that. So we want to find A1, A2, and add those together. So integral 0 to 1, 2x minus 1, absolute value dx, is simply A1 plus A2. Both of them are on the positive side, and both of them correspond to a right-angled triangle. The radius, not the radius, the base of the right-angled triangle is 2 and 1/2, and the height is 1. So the areas A1 and A2 are one and the same, and that would equal to 1/2 base times height. Base is of length 1/2, height is of length 1. So that's the base, and that's the height. So we have 1/4. So which would imply integral 0 to 1, absolute value of 2x minus 1 dx is A1 plus A2, which is 1/4 plus 1/4. We end up getting 1/2. Here's an example that uses properties of integrals. So the first one, we have integral 2 to 8 f of x dx, and that is given to be 7.3. Integral 2 to 4 f of x dx is 5.9, and integral 4 to 8 f of x dx is what we need to find. So the largest interval here is 2 to 8. So we know integral 2 to 8 f of x dx can be written as 2 to 4 f of x dx plus 4 to 8 f of x dx. Now, should we pick 4? Well, you could pick any number. It could be 2 to 5 for the first integral and 5 to 8 for the second integral. I'm doing 2 to 4 and 4 to 8 because that's what's given in the problem, and we're trying to find one of the integrals. So 7.3 would equal to 5.9 plus integral 4 to 8 f of x dx, which would imply integral 4 to 8 f of x dx equals 7.3 minus 5.9, which would give us 1.4. In the second problem, we have to find integral 0 to 9, 2 times f of x plus 3 times g of x dx. I could write this as integral 0 to 9, 2 times f of x dx plus 0 to 9, 3 times g of x dx. We can pull the constant out, so 2 times integral 0 to 9 f of x dx plus 3 times integral 0 to 9 g of x dx. And those two integrals are given to us in the problem. The values are 37 and 16. So I could write it as 2 times 37 plus 3 times 16. So 74 plus 48, which is 122. Here we have to find the integral 0 to 5 f of x dx. If f of x is 3 for x less than 3, and it is simply x for x greater than or equal to 3. Graphing this piecewise function is the best way to go. So 0 to 3, we have a horizontal line, and it doesn't include 3 for x less than 3. However, the next bit, which is x greater than or equal to 3, includes 3, so that open dot would become a closed dot, and it'll keep on going. But we only care up to 5. Because that's what the problem is. You look at it and you say, well, how am I going to find the area? A little bit of geometric knowledge is what we need. So I'm going to draw a line like that and a line like that. So now I have an area here and another area there, and another area there. By the looks of it, A1 is the area of a square, A2 is the area of a rectangle, and A3 is the area of a right-angled triangle. So integral 0 to 5 f of x dx would simply be equal to A1 plus A2 plus A3. A1 is the area of a rectangle. Oops, it's a square. Even though it looks like a rectangle, for square with length 3. So that would simply be 3 squared. We end up getting 9. A2 looks like a square, but it's actually a rectangle. It is the area of a rectangle with length 2 and width, width 2 and length 3. So we simply have 2 times 3, we get 6. A3 is the area of a right-angled triangle with base 2 and height. It's over here, and that point has to correspond to 5. So what we have, height of 2, so 1/2 base times height, we get 2. So integral 0 to 5 f of x dx is simply 9 plus 6 plus 2, we get 17. So here we have to verify the inequality without evaluating the integrals. So what we have here is 0 to 4 f of x dx. Now, f of x is x squared minus 4x plus 4, which would be x minus 2 times x minus 2 if we factor, which is x minus 2 squared. So this would imply f of x equals x minus 2 squared is greater than or equal to 0 for all x in 0 to 4, because I could put any number between 0 and 4, including 0 and 4. F of x will always be positive. Recall the property: if f of x is greater than or equal to 0, then integral a to b f of x dx has to be greater than or equal to 0. Since f of x equals x minus 2 squared is greater than or equal to 0, we have integral 0 to 4 x minus 2 squared dx greater than or equal to 0, which is the same as saying x squared minus 4x plus 4 is greater than or equal to 0. So we've verified the inequality. So here we have to use the properties of integrals to verify the inequality without evaluating the integrals. Now what we have is an integral that supposedly lies between pi over 12 and square root of 3 pi over 12. So what do we know? So we know from one of the properties, if the function f of x lies between two numbers, lowercase m and uppercase m, for x in a to b, then the integral of the function between a to b, f of x dx, has to lie between m times b minus a and lowercase m times b minus a. So we know what a is, we know what b is. It is given that m times b minus a is pi over 12, and m times uppercase m times b minus a is root 3 pi over 12. So if we can show the reverse, then we can show the inequality is true. What do I mean by that? So here we have pi over 12 integral pi over 6 to pi over 3 sine x dx is less than or equal to square root of 3 times pi over 12. So m times b minus a is pi over 12, and m times b minus a is square root of 3 pi over 12. So if we solve, we have m times pi over 3 minus pi over 6 equals pi over 12, and m times pi over 3 minus pi over 6 square root of 3 pi over 12. M times pi over 6 would equal pi over 12. Same here. Which would simply mean m is equal to pi over 2, and m is equal to, it's 1 over 2, and uppercase M is square root of 3 over 2. So we started with this part of the property, which is right here, and we want to show that part. So if f of x lies between 1/2 and square root of 3 over 2 for x in pi over 6 to pi over 3, then the given inequality is true. Now, sine x is an increasing function on that interval, which means it is going to start at sine pi over 6 and it's going to go to sine pi over 3. So what is sine pi over 6? Sine pi over 6 is 1/2, and sine pi over 3 is square root of 3 over 2. You can use a calculator. This would imply the function sine x will lie between those two values, 1/2 and square root of 3 over 2, because sine x is an increasing function on that interval. So we have shown that the function does lie between 1/2 and square root of 3 over 2, which is lowercase m and uppercase m, so the inequality has to be true. So here we're going to do the process that we did previously in reverse. So we have to use the properties of integrals to estimate the value of the integral below. We can't give an exact value, we're simply trying to estimate the value of the integral. So f of x equals x cubed is increasing on 0, 1. It doesn't have any critical values because f prime of x is 3x squared. If we set 3x squared equals 0, we would have x is equal to 0. That would be the critical number. I'm doing the first derivative test. So if that is my test point, pick an easy number, say 1. F prime of 1 is 3 times 1 squared. It's positive, so the function is increasing. That said, we have a as 0 and b as 1. Since f of x is increasing, we know that the value of x cubed has to be between 0 and 1 for x in 0 to 1. So that is lowercase m, that is uppercase m. Therefore, using the property, the integral of 0 to 1 x cubed dx has to lie between lowercase m times b minus a, uppercase m times b minus a. That is one of the properties. So we have 0 times 1 minus 0 less than or equal to 0 to 1 x cubed dx. Uppercase m is 1, 1 minus 0, So our conclusion is that the value of the integral has to be between 0 to 1. We don't know the exact value, we are simply saying that the value of the integral must lie between those two numbers, 0 and 1. Here we have another function, x cubed minus 3x plus 3. And first thing to do is we want to see if there are any maximum or minimum values. So take the first derivative and set that equal to 0. So 3x squared minus 3 is equal to 0, which would imply 3 times x squared minus 1 equal to 0, which would imply x squared minus 1 equal to 0, x squared is equal to 1, x is either 1 or minus 1. We don't care about minus 1 because our interval is from 0 to 2. So we simply look at the critical number, that is between 0 to 2. Let's pick an easy number, 1/2. F prime of 1/2 is 3 times 1/2 squared minus 3, which is 3 over 4 minus 3. That is 9 over 4 with a negative. So the function is decreasing. And pick an easy number between 1 and 2. Let me pick 3 over 2. Plug it in the derivative. 3 times 3 over 2 squared minus 3. That would be 9 over 4, 27 over 4, 21 over 4, positive number. So it is increasing. Since we have a change in direction, we have to split the integral into two parts. So 0 to 2, x cubed minus 3x plus 3 dx is the same as saying 0 to 1, x cubed minus 3x plus 3 dx plus integral 1 to 2, x cubed minus 3x plus 3 dx. Now let's evaluate the endpoints here, 0, 1, and 2. So in the function, f of 0 would be equal to 0 cubed minus 3 times 0 plus 3, we get 3. F of 1 would be 1 cubed minus 3 times 1 plus 3, we get 1. F of 2 would be 2 cubed minus 3 times 2 plus 3, which is 5. So clearly, since the function is decreasing between 0 and 1, f of x is decreasing for x in 0 to 1, and the values are 1 less than or equal to f of x less than or equal to 3. Which would mean the integral 0 to 1 f of x dx has to be less than or equal to uppercase m b minus a, lowercase m b minus a. So the lowercase m would be 1, uppercase m is 3. So 1 times 1 minus 0 less than or equal to integral 0 to 1 f of x dx. Uppercase, oh, that's 0, sorry. Uppercase m is 1, 1 minus 0. This would mean 0 less than or equal to integral 0 to 1 x cubed minus 3x plus 3 dx is less than or equal to 1 for x in 0 to 1. Now keep in mind the behavior of the function is different on the other interval. So f of x equals x cubed minus 3x plus 3 is increasing for x in 0 to 1, 1 to 2, and it increases between the values 1 here and 5. So that would be lowercase m, that is uppercase m. So using the property, since the function is between 1 and 5, including 1 and 5, we have the integral to lie between those two values. So lowercase m is 1 in this case, and 2 minus 1, b, a. Uppercase is 5 and 2 minus 1. So what we end up having is 1 less than or equal to 1 to 2 x cubed minus 3x plus 3 dx less than or equal to 5. But we can't jump to conclusion yet because we want to know the actual limit of the integral from 0 to 2. By limit, I mean the upper value and the lower value. So the original integral is from 0 to 2, x cubed minus 3x plus 3. And for x in 0 to 2, the function f of x would lie between, when you plug in 0, we end up getting 3. When we plug in 2, we have 2 cubed minus 6 plus 3, which is 5. So that is lowercase m, uppercase m. So this would mean the integral of the function on the entire interval has to lie between m times b minus a, uppercase m times b minus a. In this case, b is 2, a is 0. So we have 3 times 2 minus 0, which is 2. Integral 0 to 2, x cubed minus 3x plus 3 dx less than or equal to 5 times 2 minus 0. Ten and 6. So, what do we have here? Inequality 1 is suggesting that between 0 and 1, the limits of the integration are between 0 and 1. On the interval 1 to 2, the values are between 1 and 5. The actual value of the integral has to be between 6 and 10. Using 1 and 2, we can conclude 0 to 1, x cubed minus 3x plus 3 dx plus 1 to 2 x cubed minus 3x plus 3 dx must lie between add the inequalities. The minimum value has to be 2 because the smallest value here is 1. The greatest value there is 1, so it has to be at 2. 1 plus 1, 2. The maximum value would be at 6. But we know adding those two, this would be between 0 to 2 x cubed minus 3x plus 3 dx less than or equal to 6. Now if we combine 3 and 4, we could conclude that the smallest value of the integral has to be 2. And the largest value according to 4 is 6. But according to 3, it is 10. So the biggest of the two is 10. So the value of the integral has to be between 2 and 10. So this is a bit more involved problem, or where we have to estimate the value of the integral for the function f of x, which is x minus 2 sine x. And it's defined on the interval pi to 2 pi. Now first off, we've got to determine if this function has any absolute minimums or maximums on the given interval. So f of x is x minus 2 sine x. So f prime of x is 1 minus 2 cosine x. We're going to set f prime of x equal to 0 and solve for x to get the critical number or critical values. So well, I could simply set 1 minus 2 cosine x equal to 0, which would imply cosine x, 2 cosine x equals, or minus 2 cosine x equals minus 1. 2 cosine x is equal to 1, which would imply cosine x is equal to 1 over 2. We could use the calculator to find where it's going to be 1 over 2. We know that cosine is positive on the first and the fourth quadrant, so obviously x has to be pi over 3, and in the fourth quadrant it'll be 2 pi minus pi over 3, so that would give us pi over 3 and 5 pi over 3. Now, we can't have that pi over 3 because pi over 3 lies outside pi to 2 pi. So all we have is pi and 2 pi and 5 pi over 3. And we've got to pick an easy number between pi and 5 pi over 3. 5 pi, maybe if you have a calculator, it'll be easier to demonstrate. So we have to pick a number between pi and 5 pi over 3. We could get the midpoint between the two. So we could have pi plus 5 pi over 3 divided by 2. That is 4.18. So that value is probably here, 4.18. You can convert it to pi if you want, in terms of pi if you want. Between 5 pi over 3 and 2 pi, we will have 11 pi over 6. So we could plug it in the derivative. That was 8 pi. Oh, this is 8 pi over 6. So 8 pi over 6. Okay. So cosine 8 pi over 6 is negative. So it's going to decrease. And on that side, cosine 11 pi over 6 it's positive. So the function is decreasing between pi and 5 pi over 3, increasing between 5 pi over 3 and 2 pi. Now, so we've got to find the values as to what the, values of the function at pi, 5 pi over 3 and 2 pi. At pi, we have pi minus 2 times sine pi. Sine pi is 0, so we get pi. At 5 pi over 3, we have 5 pi over 3 minus 2 times sine 5 pi over 3. I believe that is minus square root of 3 over 2. It is, so 5 pi over 3 minus 2 times minus square root of 3 over 2. The 2's would get cancelled, so we have 5 pi over 3 plus root 3. F of 2 pi would simply be 2 pi minus 2 sine 2 pi. Sine 2 pi is 0. So we simply end up getting 2 pi. So let's start by saying what the value of the function is going to be between pi and 2 pi. So for x in pi to 2 pi, we have the function to lie between pi and 2 pi. This would imply the integral of the function, which is x minus 2 sine x, has to lie between m times b minus a, lowercase m times b minus a. M is pi, uppercase M is 2 pi, so pi times b minus a is 2 pi minus pi. and 2 pi multiplied by 2 pi minus pi. So we would end up having pi squared to 2 pi squared. So that would be the entire area of the integral. Now, the first piece, integral pi to 5 pi over 3, x minus 2 sine x dx, let's say consider. And for x in pi to 5 pi over 3, we know the function is decreasing. The function values decrease from the value pi to 5 pi over 3 plus 3, square root of 3. So 5 times pi divided by 3 plus you get 6.968. That seems to be increasing. Did I mess something up? Let's go ahead and graph this to be sure. Feels like I messed something up. Okay, that is what we have. And if I adjust the window, from pi to 2 pi, it seems to be increasing. Maybe I made a mistake in finding the midpoint. Eight pi over 6. The derivative is actually, I simply plugged it in cosine, but the derivative is 1 minus that value. So 1 minus 2, which would give us 2, so the function is increasing, and the function should be decreasing over here. I thought the derivative was just 2 cosine x, so we've got to correct that. So increasing, decreasing. So it makes sense now. So f of pi would be pi, and f of pi over 3 is 5 pi over 3 plus root 3. So for x in that interval, we have f of x satisfying that condition. It could only mean that integral pi to 5 pi over 3, x minus 2 sine x, which is our function, must lie between lowercase m times b minus a, uppercase m times b minus a. Lowercase m here is pi, and uppercase m is 5 pi over 3 plus root 3. So pi times 5 pi over 3 minus pi, pi times 5 pi over 3, x minus 2 sine x dx less than or equal to 5 pi over 3 plus root 3 multiplied by 5 pi over 3 minus pi. That would end up giving us 2 pi squared over 3 and that's what we would have. Okay, so that's another limit. And the next integral that we have, 5 pi over 3 to 2 pi, and the function is decreasing here, so x minus 2 sine x dx, and for x in this interval, we have f of x to lie between 5 pi over 3 plus root 3 and 2 pi. So that would become our lowercase m, and that would be uppercase m. Since that condition is satisfied according to our property, we would have the integral pi 5 pi over 3 to 2 pi f of x dx has to lie between lowercase m times b minus a, uppercase m times b minus a. Lowercase m is 5 pi over 3 plus root 3, 2 pi minus 5 pi over 3, two pi multiplied by 2 pi minus 5 pi over 3. So we would have 5 pi over 3 plus root 3 multiplied by pi over 3 2 pi times pi over 3. So that is another inequality that we have. So while we have the inequalities and we can compare the lower endpoints, pi squared, 2 pi squared over 3 in inequality number 2, and that we can say that the lower endpoint has to be pi squared. So the lower endpoint for the integral is pi squared. That is obvious. Now we could do the comparisons here and find the lower integral for, the upper endpoint for the integral. But even though we can compare the inequalities to get that value, we can also realize that the function has an absolute maximum at 5 pi over 3, which would imply between f of x has to be less than f pi over 3 and whatever value we have at pi, because f of pi over 3 f of 5 pi over 3 is the maximum value of the function. So f of 5 pi over 3 is simply 5 pi over 3 minus 2 sine 5 pi over 3. And f of pi is simply pi. So we would have f of pi over 3 minus root 3, we've done this before, and pi. Now this is a new lowercase m, uppercase m. So since f of x satisfies that for x in pi to 2 pi, we have the integral from pi to 2 pi f of x dx to be less than m times b minus a, uppercase m times b minus a. So which would give us pi times b minus a, 2 pi minus pi, less than or equal to integral pi times 2 pi x minus 2 sine x dx, less than or equal to 5 pi over 3 minus root 3 times two pi minus pi. So that minus root 3 comes from sine pi over 3. Can verify that. Sine 5 pi over 3. It's negative. Negative of negative would be positive, so that'd be positive. So positive. So that would be pi squared less than or equal to pi to 2 pi x minus 2 sine x dx, which should be less than or equal to 5 pi over 3 plus root 3 times pi. So if we include that argument, we can see that this would be the upper bound for the integral. So the integral has to lie between pi squared and 5 pi over 3 plus root 3 times pi.